All right. Hello, everyone. So this week, the topic we're going to talk about is causality. And in terms of context, we've been developing this unambiguous language to describe random phenomenon. And this week, we're going to turn that language towards causality in order to define what we mean by causal relationships, which are really what's of interest most of the time in the real world. So our picture now looks like this. So we did a bunch of probability theory, random variables, and all sorts of stuff like that. And then we talked last time about estimators and inference. So how do we guess about the stuff that's going on in the real world, and how do we quantify our level of uncertainty in those guesses? Again, drawing upon all this, like all the tools that we built in probability theory. And today we're going to kind of leave that be for a sec and come back to probability theory. And develop some notion of causality based on probability theory. That then later we're going to come back to statistics and then say how can we estimate these causal quantities. So right now we're just going to define what we mean by causality in terms of something called potential outcomes. So fundamentally we're asking, what does it mean for X to causally affect Y? So here's an abstract. And it says, we sought to estimate what the incidence of pregnancy by 26 weeks post-randomization would have been if we shifted each participant's probability of taking aspirin or placebo each week by some odds ratio, whatever. This is really the key, is that causality is about questions of what if, what would something would have been versus what would it have been in another case. So I think sometimes we have like a naive notion of causality of like before and after, right? So let's say I'm sitting around and then I take some drug and then I get a headache. I think, well, maybe the headache was a side effect of taking that drug. That drug caused me to have a headache. So it caused the headache. But that's actually a naive view of causality. Causality doesn't have to do with a comparison of before and after, per se. It really has to, causality has to do with a comparison of what would have happened if I had done something else. So I can say the drug causes the headache if in an alternate reality I hadn't taken the drug and I didn't have a headache, right? So this is getting more at what we mean by causality. And something that's really interesting about this is that it's actually impossible to observe the causal comparison. So of course I can either take the drug or I can not take the drug. But I can't do both, right? I can't actually see what would have happened to me if I did one thing versus to me if I didn't do that thing. But in order to define what we mean by causality, we need to be able to imagine both of those scenarios, which we sometimes call counterfactual scenarios. So the fact is I didn't take the drug, right? Counterfactually, what would have happened if I had, right? Or the fact is I took the drug. Counterfactually, what would have happened if I hadn't? Right? So that's what we need to kind of stretch our minds in order to imagine, in order to define a rigorous notion of causality. So we call these counterfactuals, like I said. Introducing a little bit of notation, I'll tend to use big letter A to denote a random variable that indicates whether or not I was actually exposed to some kind of exposure or intervention or treatment. These are all words that I'll use kind of interchangeably. So here, for example, taking a drug versus not taking it. And I want to know, does that cause the headache? And in terms of the outcome, I'll usually use the letter Y to denote that outcome. And really there are two outcomes. There's what would have happened if I take the drug. So I'm going to call that Y1. Oops, sorry. And there's what would have happened if I didn't. So these are actually two different random variables. And this notation, I mean, maybe it's not the best to use the parentheses, but this is the way it's kind of done in the literature. So Y1, Y0 are two different random variables, basically, that represent what would have happened under different conditions. So we'll clarify this a little bit here. So you can think of, in terms of like a table for a data generating process, we'll call it causal data generating process we have for each person. So maybe this is me and this is you and this is my friend. We have, did this person actually take the drug or not? So maybe I didn't, and maybe you did, and my friend did as well. And then we have the outcomes under both cases. So I didn't take the drug. So this is the outcome I actually experienced. But this is the imaginary outcome. This is what would have happened if I had. Okay? And so sometimes people call this like the science table, or the potential outcomes table. And the key is that you have to imagine that for every person, or like let's say for you, right? You took the drug. So you actually experienced this outcome. Whatever. These numbers maybe are indicate like the severity of a headache or something like that. But you have to also imagine what would have happened if you didn't, which is what Y0 represents. So what we observe, like I said, is the potential outcome that actually corresponds to the treatment that that person actually got. So I did not get the drug, so my observed outcome is 5.5 severity of headache. I don't get to see what would have happened if I didn't, right? Similarly, for this person, we don't get to see this 9, we only get to see that 9. And for this person, since they got the drug, we only got to see the value in this column, which is the 8. And so when we actually look at the data, like the observed data, it doesn't have these columns Y0, Y1. We just see Y, right? So these are imaginary. These are things we have to kind of keep in the back of our head. The what if kind of question when we're analyzing the data. So if we think about data generating processes, what is the data generating process that makes a table like this? We think about causal data generating process. So in a causal data generating process, we have Y1 and Y0, which are different random variables. And we can give them both, we can give them each different nodes to represent them. And so I would write that in R, if I were to make up a data generating process, I would say, okay, so each person, I'm going to say has some kind of baseline covariates, like maybe their age, which I'll represent with X, and, you know, just picking arbitrarily that, let's just say that's normally distributed. And then do they take the drug or not? So here, the probability of taking this drug is determined based on their age. So maybe older people are more likely to take it. And then here, Y0 is what for everyone, regardless of their age, what would have happened if we made them not do it, not take this drug. So here we're basically saying that the outcome for this person depends on their age. And it's like 2 times their age if they don't take the drug, and if they do take the drug, it's 1 times their age, and both of those are added to some noise. And so when we generate the data from this causal data generating process, we get, you know, the age, maybe this is like z-score age because there's negatives, and then we have whether or not they were exposed, they got the treatment, and then we have what would have happened if they didn't get the treatment, what would have happened if they did get the treatment. So we get both of these from the causal data generating process. Now, in reality, we don't get to see that causal data generating process. We get to see data from, we get to see observed data. So what does that look like? Well, first we have to construct the observed outcome. So the observed outcome corresponds to whichever one of the potential outcomes is appropriate for the treatment. So here I do with if-else. So basically, if A for this person was 1, then the outcome we get to see was the Y1. If this is 0, then the outcome we get to see is the Y0. And then I get rid of those Y1 and Y0 columns. So the observed data generating process, when I sample data from that, you know, I kind of hide these things, right? So Y1, Y0, and A all together determine what the observed outcome is, right? Whereas Y1 and Y0 by themselves don't depend on A, right? They're in this DAG, they're independent. But Y depends on both of them. And so here we get to see that we only get to see the observed outcome. We don't have these potential outcomes anymore. Those are hidden from us. So I think a useful way to conceptualize this, which we'll see in the next lecture why this is very, very helpful, is to think of observed data generating process as transformations of causal data generating processes. So here's our causal data generating process in code, and here's the corresponding DAG for it. And we can think of let's come up with a function that takes a causal DGP and outputs an observed DGP. So here I've written this function in R, which takes another function, takes this function and outputs a function and the function that it outputs is just calling this thing and then taking the observed outcome and then dropping the potential outcomes, which is the process that we saw before. And then I can generate the observable DGP, so this is itself going to be a function from that causal DGP, and now I can sample from it like this. So the data we get to see are a sample from the observable data generating process, which itself is some kind of transformation of the causal data generating process. And this transformation is exactly, which I did note with this kind of script O, is the just setting the observed outcome based on what the actual value of the treatment was, and then dropping the potential outcomes. That's all that's happening in this transformation. All right, so instead of drawing these DAGs separately for the causal data generating process and an observed data generating process, there's a handy way to combine them called single world interaction graphs. So you can, if you want to learn more about these things, you can look them up. But it's kind of a handy way to not have to draw separate DAGs for everything, and kind of unify the perspectives. So the way this works is we have here we'll write. Well, I guess let's start. Yeah, let's start here. So we'll write for the outcome y parentheses a. So here a can be either 0 or 1. We're just writing a to represent both of them because we don't want to draw like two separate like y0 and y1 nodes anymore. We just want to say kind of put them together. So we just draw the one node, and so you can imagine this like this is y. This one node actually stands for two things, right? Like y0 and y1 right behind it. That's kind of what this one node is standing for. These two things. And now so what goes into it? So if we look at our causal DAG, remember before we had it looking like this, where some baseline information determined what treatment somebody gets, but it also determines what outcomes would have been under either of those treatments. So x goes into y1 and y0. So here we have x going into ya. So this arrow x going into ya basically means that x goes into y1 and y0. And then what else goes into ya? Well, little a. So here we have little a going into ya. And so that says like basically this thing, if this is 1, right, then this will end up being this guy, y1. And if this is 0, then this stands for this one, right, y0. So a just kind of sets which one of these we're looking at, either this one or this one, depending on what little a is. Okay. And the cute thing about the single world interaction graph is this kind of tie between big A and little a. So we've kind of split the exposure or treatment node up into two halves here in the middle, right? And the reason we did that is because we're kind of trying to represent two things at once. So we're representing in the causal world, which is this, right? In the causal world, the value that somebody gets for the treatment doesn't actually influence what the potential outcomes are, right? So I can observe what would have happened in both cases. It doesn't matter what actually happens for the exposure. I can still see what would have happened in both cases. But in the observed data generating process world, this value, little a, is actually set by what happens. So what happens is a. So let's say a, we get a equals 1. Then this actually passes through and determines this is 1, and therefore the one we get to see is this one and not this one. On the other hand, if depending on what the covariates are, whatever, then this person chooses to not take the drug, not get the treatment, then this is set to 0, and the version that we get to see is the y0. So it's this one and not that one. So that's how this kind of works. It's just a one picture that's trying to represent all of this information. So we have the observed treatment and the kind of like a forced treatment next to each other to indicate that in the observed world, these things are the same, right? That the value of treatment that somebody gets is actually what ends up determining which potential outcome you observe. But in the causal world, where we can observe both potential outcomes, we can manipulate little a independently, and force it to be whatever we want it to be to get either potential outcome. So it's just a kind of a nice notation in order to represent both the causal DAG and the observed world DAG in one picture. All right. So now that we have a causal model, so to speak, or a causal DAG and single world interaction graphs, we can define what we mean by causal effects. So a causal effect is just an estimand. So we've been looking at estimands before, like the mean of something or the variance of something. So it's just an estimand, but it's defined on the potential outcomes. So for example, the average treatment effect, this is by far the most kind of common causal estimand that you'll find in the real world that people are interested in, kind of like the canonical thing that everyone starts with. This is the difference in average counterfactuals. So it's the mean of y1 minus the mean of y0. So this is basically like, what if we took if we took everyone and we did not treat them, what would the average outcome be? So for example, like if y represents lifespan, this would be like, what is the average lifespan if we gave everyone the placebo, versus what's the average lifespan in the population if we gave everyone the new drug that we're testing. So the difference of this reflects how much this drug works. This is the causal effect, is this difference, which is, if you remember our picture of like a little person, and then there's these kind of counterfactual worlds where either you take the drug or nothing happens, right? And then we see what happens, where we're saying this is y1 and y0. This causal effect is a way to quantify, right, the difference between these two potential outcomes, averaged over the population. So in terms of code in R, if we had this is a causal data generating process, how can I compute the value of this estimand? Well, I just draw, same way we do for general estimands, we just draw a ton of data from it, and then we take the mean of y1 and we subtract off the mean of y0. So in this case, the number we get is about 0.00125. So this is what I already said. What does this represent? It's what's the average outcome? What would it be if we gave everyone the treatment versus what would it be if we gave no one the treatment? So again, we're thinking in terms of counterfactuals, what would have happened, and that is what we mean by causality. So there's also this thing called the naive ATE, and we're going to dig a lot into this, but first we'll just define it. So here's our data generating process, where I've kind of combined both like so here I have, these are the potential outcomes, and then this is the observed outcome. I've just kind of put it into one data generating process. If I wanted to have the observed, I would just ignore these. If I wanted to have the causal data generating process, I would just ignore the observed outcome. So here I'm just showing it all together. And I'm defining two different estimands. So the first one is the ATE that we saw on the previous page. It's what is what's the difference in mean outcomes if everyone were treated versus if no one were treated. And then down here I've defined this thing that I'm calling the naive ATE, which is the expected value of the observed outcome conditioned on treatment being 1, and the expected value of the observed minus the expected value of the observed outcome conditioned on treatment being 0. So what does that mean? So let's see what I've got on the next slide here. Yeah, so let's dig into it a little more. Visually, if we made this table that we could get by sampling, this number here represents the mean of this column, right? What does this number represent? This number represents not the mean of this column, but it represents the mean of these values, where these values are the ones that correspond to a 1 in this column. And of course, these values are these values, the 9 and the 8 are here, right? Because if this is a 1, then that 9 comes from here and this 8 comes from here. But what are we not getting? We're missing this 3, we're missing whatever's here, we're missing whatever's here. So this average is like an average of the y1s, but we're missing a whole bunch of data, right? We're ignoring certain cells. So it's not the same thing. And this is super, super key, okay? So the expected value of a potential outcome is not necessarily the same as the expected value of the observed, conditioned on, whatever condition is kind of like defining that potential outcome. These are just different values. So this average versus this average of this kind of subset of values, not the same thing. So the average treatment effect asks, what if, right? We already saw this. What would the average outcome be if we gave everyone the treatment versus if we gave nobody the treatment, and what's the difference? So then we saw this naive thing is different, but how do we interpret it? So this thing is, what's the average outcome among people who decide to take the treatment? So this is not, what if we forced everyone to take the treatment? What's the average outcome in the whole population? This is, what's the average outcome among the people in the population who did take the treatment versus the average outcome in the population of people who did not take the treatment? So that's exactly what I was showing here, right? This average, I'm averaging only across the subset of the population who decided to take the treatment. Versus here, I'm forcing everyone kind of to take the treatment. I'm asking, if we made everyone do it, what would the average be? So these quantities are different, and sometimes very different. But in theory, they're the different estimates entirely. So here's an example that maybe will help make this more concrete. So let's say that older people are more likely to take statins. So statins it's a super common class of drug that lowers cholesterol. And let's say we have a data set. And in that data set, we have the average cholesterol levels of people who have been given statins for a year. And we can see that that average level is higher than the level of people who haven't been given statins for a year. And the question is, do statins cause higher cholesterol? How do you explain this? So this is directly related to this question here, right? So I would think of this like, let's draw a picture. Okay, so we have the statins, which is like, that's our exposure, A. And then we have the observed outcome, Y, is cholesterol. And we want to know if statins causing cholesterol. So what we said we observed in the data is that for people who have the statins, let's say they're on a scale of like 0 to 10, what's their cholesterol level? The people who are taking the statins, their cholesterol after a year is like, say, like 9 and 8, and the people who are not taking the statins, after a year, they decided not to do it, and a year later, we look at their values, and they tend to be lower. So does this mean that the statins, people who deciding to take a statin actually actually increases cholesterol? That's very counterintuitive, because we think statins, like the whole point of them is to decrease cholesterol. So why is it that people who are taking them have higher cholesterol than people who aren't taking them? And the answer is that this is really not the full picture, right? We need to think about the potential outcomes. So what we need to think about is the table that looks like this. So we have statin, these are the same people, and then we have, what is the cholesterol if they had taken statin? If statin. And then what would have their cholesterol been if no statin? So here this is like A, and this one is if statin, that's Y1. And then we have here, this is what we usually call Y0. And what are we observing over here? Well, this 9, this person did take a statin, and they have a 9, so that one would end up here, and this 8 would go here, right? And this 5, this is for somebody who didn't take statin, right? So we know that that one is here and the 4 is here. But we don't know what goes here, what goes here. We don't get to see what goes here, and we don't get to see what goes here. So does it mean that if looking at this data, can we say that taking a statin causes higher cholesterol when we think it should be less? No. What's really going on? What's really going on is probably, if we could observe these question marks and see what they were, maybe it would be like this. So maybe these would be 10s, and maybe these ones would be like a 3 and a 2. So we see that actually, if let's look at it the other way, going from statin to no statin going from no statin to statin actually lowers cholesterol. So if you start taking statins versus if you hadn't, your cholesterol would actually be lower if you had taken the statin. So people should take statins to lower their cholesterol, which is what we think. But the problem is that we're not observing these values. So what's going on here? Why are these higher than these? Well, maybe there's some other variable, right? Like, I don't know, age, which we mentioned. So now we're gonna get into formalizing this in the next few slides. But maybe really what's going on is that people who are old, relatively speaking, tend to have just higher cholesterol in general, and also tend to take statins. So when their cholesterol is high, they're more likely to want to take a statin to lower it. Whereas young people, their cholesterol is kind of low already. They don't really care about lowering it, and so they don't do it. But if you just ignore this kind of difference, then in the data it looks like people who are taking statins have higher cholesterol. But you can't. That is not really the appropriate comparison. So this comparison, if you just looked at the average here, right, this would be this naive ATE, where you're just looking at the average of Y. Give among the people who are taking it, right, minus what's the average among the people who are not taking it. But that's not what you want to do, because these people, the people who are taking it and the people who are not taking it, are systematically different, right? What you actually want to look at is this, if you could somehow get to it, you would want to imagine what would the world be like if we made everyone do it versus if we made nobody do it, right? And then compare these average counterfactual outcomes. All right, so let's get back to here. So do statins cause higher cholesterol? No, I mean, statins should lower cholesterol in general, and we kind of explain how that might happen. So let's dig into this a little more with a simulation. So let's say that this data generating process models a problem. So now we have age, we have whether or not somebody takes a statin, we have the two potential outcomes, and we have the actual observed outcome. And let's draw this some data and explore it. So we take this, and we can put it in R here. Let's just draw some large amount of data here, and let's plot let's just look at the age distribution among people who are taking statins versus not taking statins. So let's do that with geom density, and we can look at the age distribution and then have two different distributions depending on whether they're taking statin or not. Oops, yeah, so I forgot to make this a factor. There we go. Okay, so we can see that there's, at least in this data generating process, there's actually a pretty sharp difference. So people who take statins tend to be older. So their average age is like 65, whereas people who are, so here in our population we're only looking at people who are between 50 and 70, but whereas people who are not taking statins tend to be much younger, so between 50 and 60 or so. So that's certainly what we kind of expected based on our intuition. And now we can also look at, so let's look at in reality, what would be the population average outcome if we forced everyone to take statins versus not? Or actually, let's just look at the distribution of outcomes in both of those cases. So let's look at what would the outcomes in general, what would that distribution of outcomes look like if we forced everyone to not take statins. So we'll do that one in black. And then compare that to what would it look like if we forced everyone to take statins. So what we see here is that if we forced everyone to take statins, which is the red distribution, the entire curve kind of shifts to the left. So we have systematically lower cholesterol when everyone is taking statin, which makes sense. That's the point of statins. They're there to lower cholesterol, right? So that's what we see. But of course, I mean, this is a simulation. We can't really observe these two curves. Like if we could, then that would fix the whole problem of causal inference. But we don't get to see these two distributions, right? We only get to see we only get to see this observed outcome, not these potential outcomes, right? So if we can look at just the observed outcome and try to get at something. But so let's first just calculate the difference in means here, which is the causal average treatment effect. It's the average LDL if everyone were taking statin versus the average LDL. LDL is just a measure of cholesterol, by the way, if I didn't say that earlier. We see here we have a negative number, which means that this is smaller than this is. In other words, that taking statins lowers cholesterol, right? So taking statins on average, if everyone were doing it, cholesterol would be lower by 1 point or so, like 1.2 or whatever. So that's good. So people should take statins. But what happens if we just ignore the fact that we don't have these outcomes? Let's just look at the naive ATE and look at the differences in the mean LDL observed LDL among people who are taking statin minus LDL among people who are not taking statin. What does that look like? Well, I messed up my code here. There we go. It's a positive number. In other words, the average outcome among people who are taking the statin is higher. The people who are taking the statin have on average higher cholesterol than the people who are not taking the statin, which, if you weren't really thinking carefully, would lead you to believe that statin actually increases cholesterol, but that's not the case, right? Actually, it decreases cholesterol, but here it looks like it's increasing cholesterol with this naive analysis. And of course, what's going on is actually just that we're not really getting a fair sample, right? Like this average is actually a subset of these numbers, and the numbers that we're ignoring are systematically higher or lower in a particular way that makes it look like this. So let's wrap this up and go to a cartoon that's going to illustrate that point.